Hey guys, welcome back to the shop. It's going to be a little bit noisy in these videos. My furnace is just cranking away. It's brutally cold here right now. I think it was minus 10 degrees Fahrenheit last night. That's like, I don't know, minus 15, minus 20 Celsius, something like that. Brutally cold. Anyway, we're working on this HA-250 fully automatic bandsaw. And it says Kaiser Johnson, but this saw was 100% made in Japan by Amada. And this particular saw was built in 1979. But to give you an idea of how good this design was, you can still buy a brand new HA-250 from Amada, and it will look pretty much identical to this saw. The only big difference is they're almost all variable speed pulley now instead of step belt. I think they all are and have been for a while. And then the vice jaws, this saw uses a rack style with a little pawl that drops in the rack. The newer saws have full length retractable cylinders for the vice jaws. Otherwise, they really haven't changed them very much. Alright, so the main project for today is to replace the coolant pump. So this is the main drive motor here, 2.2 kilowatts, 4 horsepower. That drives the gearbox that rotates the blade, it does everything. And then it has a small gear pump right here that pumps the coolant. And it does work, but periodically it will fail to prime. And the saw will just run and run and run, and the coolant will never pump. And the only way I can make it work is to use like compressed air to force coolant into the pump and get it to prime. So it's a gear pump, but it's lost its ability to self-prime all the time. And I've tried to find parts for it, and I've tried to find a direct replacement for it, and it seems to be completely obsolete. So if I'm going to have to go through all the trouble of modifying the brackets to put a different pump on there, I think we'd be better served just to go to an electric pump. So that's the plan for today. So there are a lot of companies that make aftermarket parts for these bandsaws. They were very popular saws. They made a ton of them. And there are some aftermarket coolant pump upgrades. The problem is that they all seem to be single phase 110 volt pumps, and they basically just tap into the control circuit. There's a 110 volt control circuit for all the contacts inside the control cabinet, and then you basically have to flip a switch every time you want the pump to come on. So that would work, but I don't think it's a very elegant solution. So what we're going to do is use this right here. This is a 1/8 horsepower 3-phase coolant pump. It is made by Yeong Chyung in Taiwan. It's I think it's been used, but maybe very lightly. I bought it on eBay for like 10 bucks. It can be set up to run on 480 or 220 volt 3-phase. I've gone ahead and switched it over to 220. I made this little bracket here that it will mount to, then we can mount the bracket to the bottom of the machine. I've got a contactor, an overload heater, a 3-pole fuse block, some spade terminals and ring terminals, a roll of 16 gauge wire, a couple of cord grips, and some 16 gauge SOOW cable for conductor, and then some DIN rail to mount the contactors, and then hose clamps. We're going to go ahead and replace all the hoses on the machine. The coolant just turns that PVC hose super hard and brittle, and eventually it starts to crack, so we're just going to replace all of it while we're in there. Okay, so I made a copy of the original machine schematic, electrical schematic, and I added in the coolant pump and the contact here, as well as the overload. So I went ahead and made a standalone schematic for the modifications that we're making. So we're not doing any changes to the blade motor and the hydraulic motor, other than I am going to change out the contact and the heater for the motor, and I'll show you why. They're just in pretty bad shape. The contactor's been changed once before. I think the heater is original and it's in rough shape. So the coolant pump is being added. We're going to add a fuse block here. That's this right here. It's a 3-pole glass fuse block. It takes regular 1/4 by 1.25" fuses, and we will run 1 amp fast blow fuses. National Electric Code allows us to go up to 300% of the motor full load amps. This is a 1/8 horsepower motor, so the full load amps is like 0.38 amps. So 1 amp's just under 300%. The reason we're allowed to do that is because the motor is going to have some large startup current, so you're allowed to go up to 300% on fast blow fuses. There's different rules for different types of overcurrent protection, you know, inverse time breakers and slow blow fuses. Anyway, 300% on fast blow fuses. This is the new contactor that's going to be installed here. Looks like this. It's made by Fuji. It's just a simple 3-pole 110 volt coil contactor. It's good for 9 amps. Then we'll add a thermal overload. That looks like this. And the thermal overload basically attaches to the bottom of the contactor, and they essentially function as one unit. So the main incoming circuit breaker here is 20 amps. So this is, I think, 12 gauge wire here. So we're going to tap into the terminal strip where the L1, L2, L3 come in, and then we will use 16 gauge wire here to the fuse, and then everything running out to the motor will be basically 16 gauge. The motor wire is SOOW cable, and the S means it's good for 600 volts. The OO means that both the outside jacket and the inside wire insulation are both oil resistant. So this portion of the circuit right here is called a feeder tap, and a feeder tap has special rules according to the electrical code. The reason is that the overcurrent protection is not at the start of the branch circuit. So normally, you know, you'd have like a circuit breaker box or whatever, and you'd have whatever 100 amps coming in, and then all the breakers would clip into the box, and your overcurrent protection is at the start of the circuit, and you don't have to worry about this. But because the fuse or the overcurrent protection device is after the start of the branch circuit, we have to follow the rules as far as the feeder tap conductor size. So basically the rule is that these conductors here have to be able to carry 10% of the current that they're tapping into. So this is a 20 amp circuit here. These wires right here have to be good for at least 2 amps. And they also have to be less than 10 feet or 3 meters in length. There's other rules too. They have to be protected either inside of a panel or a conduit, yada yada. There's also another type of feeder tap that can be up to 25 feet long, and in that case you have to have conductors that are good for up to 1/3 of the current that they're tapped into. But these are going to be relatively short wires, so we'll use the 10% rule. And the wire that we're going to use is this. This is 16 gauge MTW wire. See right here listed as MTW. That's machine tool wire. And you don't have to use machine tool wire, but it's nice to work with because it's stranded and it's very finely stranded. So you want stranded wire for a machine tool. You never want to use solid wire. The reason is solid wire tends to fatigue and break, whereas stranded wire, it has a much longer fatigue life. I've seen control panels that were built with solid wire that had to be completely rewired after a few years of service. I think the one I remember was on a parts washing machine, and the thing just sat there and buzzed the whole time it ran, and it eventually started to break all the solid wires and short things out inside the panel, so it had to be completely redone. Anyway, MTW, and this MTW inside of a control panel is allowed to carry up to 10 amps. So we'll use 16 gauge wire everywhere, so 10 amps is well above 10% of 20 amps, so we're good to go there. Now, like I said, motors have special rules according to the National Electric Code, and you have to follow those rules. So the rules say every motor has to have an overcurrent protection device that protects the wire from short circuits. It also has to have a thermal overload protection device that protects the motor from overloads as far as pulling too many amps. So if the motor stalls out or whatever and the amperage starts to climb, it's going to overheat the windings in the motor, so we use the thermal overloads to prevent that from happening. So you have to have both overcurrent and thermal overload protection for the motor. Each of these does a separate function, and either one of them can do both. Now there are motor starters that have all three of these things built in, and it's basically a complete unit, but in most cases you're going to find that they're separated out. Now if you have a variable frequency drive, typically speaking you would not need a thermal overcurrent device, because the variable frequency drive knows the full load amps of the motor and it's monitoring the amperage. Now the exception is some old VFDs don't have that option, and if you're using a VFD to power multiple motors, you have to have a thermal overload for every motor. But that's not something that typically we do in a machine tool application, but you will see it in like conveyors and stuff. So anyway, it's something to keep in mind. So basically we're not going to worry about anything that was put in place by the machine builder. We'll assume that they know what they were doing, but any modifications that we make to the machine have to follow the code. Now down here at the bottom I have shown the logic part of the circuit. So that's this section right here on the diagram. So basically there's 110 volt potential between rails 1 and 2, and there's some logic here that determines when each set of coils is going to be turned on. So different things turn on the hydraulic pump, different things turn on the blade motor. We basically want the blade or the coolant pump to turn on anytime that the blade motor turns on, so we'll just parallel that coil with the blade motor coil. So over here are the thermal overloads. So each thermal overload has one normally closed and one normally open contact, and basically when this thing heats up too far, it's going to trip this thing right here, and that will open the normally closed and close the normally open. And so we run all three of those in series to complete this circuit. So basically if any of these thermal overloads is tripped, none of the motor contactors can be closed. Okay, I ran into a classic trap for young players. This pump right here, made in Taiwan. The machine, the bandsaw, made in Japan. I took the old barb fittings out of the old pump, but they are 1/4 inch pipe thread. The new pump has 3/8 female thread, so I need a bushing to reduce that down. Now that would be no problem, except that these are BSP pipe threads, British standard, and this is a really common problem here in North America, because these threads look very similar to US standard pipe threads, but the pitch is different. This actually has 19 threads per inch. So here's an 18 threads per inch thread gauge, and yeah, see how it just won't quite go down in there? That's because there's actually 19 threads per inch on this fitting, and the female 3/8 are also 19 threads per inch. Here's the call out right here in the machinery's handbook. So I'll order a couple bushings from McMaster-Carr and we'll have them tomorrow. The pump is wired and plumbed. I'll leave this cover off until we make sure that there's no leaks. So we've got a problem. I got the wiring completed and I was doing some testing with the pump, and it just keeps tripping out the thermal overload, and I took the pump apart, and the bottom bearing was kind of chewy, so I thought I could just replace that. But while it was on the bench, I did some electrical testing, and you can see what I found. So we got basically 1.1 k ohms there, 1.1 k ohms there. Yeah, 62 ohms. So the motor is set up right now in a delta configuration for 240 volts or 220 volts. I just followed the little schematic inside the cover, and each of these windings should be basically identical. So anyway, my $20 eBay bargain is not a bargain. So by the way, this is also a valuable lesson about why you need to have a thermal overload for your motor. You know, remember the fuses that we're using are 3 times the full load amps of this motor, so it's going to have to break down pretty far before it blows the fuses. But the thermal overload will trip out as soon as it gets above the full load amps, and that's what we need because we don't want this thing catching on fire. So this is the motor overload off of the hydraulic motor that I replaced, and you can see it had this plastic cover that's kind of broken, and the tabs were missing, and then the plastic's all broken here around one of the terminals, so it's had a rough life. This is, I'm sure, original to the saw from 1979, so 40 years old. So internally these things are super simple. There's 3 bimetallic strips here, and wrapped around each bimetallic strip is a coil of wire, and the current passes through the coil of wire and out to the motor. And if the motor starts to pull too many amps, this coil of wire heats up, and it causes the bimetallic strip to creep over to the right. And when it creeps over, it pushes this little phenolic tab, and when the tab kicks over, this little metal lever arm is going to shoot forward. You'll see right there, it tripped. So when it trips, there's a small contact here on the side, and it breaks the normally closed and closes the normally open. And then all we have to do to reset it is push this button, and it will close the contact again and reset the arm. And it won't reset until these bimetallic strips basically cool off and relax to their nominal position. Now there's this cam here in the front that you can adjust, and that basically sort of fine-tunes the amperage that the overload will trip at, and all it does is just changes how far this lever has to tweak over before it will trip. Alright guys, it's been about a week and I've got the new pump in. I've also come down with a cold, so I'm sorry about that. I ordered the pump from these guys, Ison Machinery. They're like a importer of all things Taiwanese out in California. I think it was about $120 shipped to my door, and we'll go ahead and check it out real quick. So 90 ohms. Seems like everything's good to go. The phases are supposed to be balanced within, you know, a few percent. And you remember on the old one we had like 1.2 k ohms or something crazy. So definitely something wrong with the winding on the old pump. So as far as I can tell, the new pump is identical functionally, except they found a way to cheap out and save, you know, a couple nickels on the BOM cost. So instead of having a nice metal plate, they just got this cheesy plastic sticker here for all the motor data, and you know that's never gonna last, especially on a coolant pump. That's really crusty. So I went ahead and pulled the tag off the old pump and installed it on the new pump, and this is a nice metal tag that's been engraved. This thing will be around for years and years, so you know, gotta be nice to the next guy because chances are it's gonna be you. Okay, I've got the new pump installed in its final location. All the plumbing is done. Okay, here's a final view of the electrical panel. So here's the replacement contactor for the hydraulic pump and the new contactor for the coolant pump. These are the overload relays here. So I've got this wire 9.1 and 9.0 daisy chained through
the normally closed contacts, and then comes up to the coil side. And the coil for the main motor and the pump motor are parallel, just like on the schematic. And then you see my overcurrent protection here, the fuse block. It's tapped right into the L1, L2, L3 coming out of the circuit breaker over here. Then this is the SO cable here that runs out to the pump. So everything looks pretty tidy. So the only caveat here that I haven't mentioned is that this machine is capable of being wired for 480 volts. You have to change all the motors from delta to Y, and you have to change out the overload heaters for the lower amperage. But this fuse block and these glass fuses are only rated for 250 volts. So if someone wants to convert this machine over to 480 volts, they're going to have to come up with a different overcurrent protection device. Okay, so the only other thing I did is I replaced these door seals here with some new foam tape. It's got an adhesive back. The old seals were these rubber strips that were glued to the frame here, and they were all peeling off. Okay guys, thanks for watching. This video has probably gone on for way too long. So as you may have guessed from the videos on the channel here, I really like electrical work and I'm very comfortable with it. And I think that in another life I probably could have been pretty happy as an electrician. It just didn't work out that way for me. I really like the cleanliness of it. You know, all these parts are just cookie cutter parts. You buy them from whatever supplier. You put them together according to the code book and everything works. You don't have to make a bunch of stuff. You just spec what you want, you buy it, you put it together, and you're good to go. So people ask me from time to time if I have any advice for people who want to get into repairing machine tools or like the industrial side of repair. And one thing that I will tell you is you should try to learn as much as you can about the electrical side of the industry. I can't tell you the number of people that I've met who were very smart, very capable guys, and they were masters of the mechanical aspect. You know, you give them a mechanical problem and a little bit of direction and they've got it figured out. But as soon as they run into an electrical problem, they just have no idea what to do. And that is a major disability, and it's only going to get worse. You know, things are only going to become more electronic. Things like CNC controls and, you know, guarding and logic involved with that, those things are here to stay. So as far as I'm concerned, there's no shortage of work for guys who can do both the mechanical and the electrical things. You know, machine tools are pretty electrically integrated and you really need to have some knowledge of those systems.